After doing linear programming for maximization and minimization, now we are going to do the non-linear programming, and in this video we will focus on the maximization process. So for the non-linear objective and constraint functions, linear programming cannot be used. Therefore, we use the non-linear programming, as the title goes that it deals with the non-linear version of the functions, may it be an objective function or a constraint function. So there can be non-linear inequality as well in this case, in addition to the equalities, as we have seen that when the constraints are there can be lesser or greater than sign because of the possibility of a maximum and minimum value within a constraint. Now the process is basically similar to the other versions of programming, that is linear programming or optimization, to a certain extent. However, there is a slight difference, as you will see, and that difference is based upon the terms and the conditions provided by Kuhn-Tucker. These are the Kuhn-Tucker conditions, 1951. These are the conditions that we will use in order to maximize or minimize a certain objective function by using the nonlinear programming. These conditions are similar to the first order conditions that we have studied before in calculus-based optimization that required the first order derivative to be equal to 0. So here Kuhn-Tucker conditions for maximization are being explained. These are in general terms. Let us assume that we have j number of variables and there will be j number of conditions for that. So the number of conditions that we will use will be equal to the number of variables. For example, if j starts from 1 and goes to n, and if we have n variables, then we will have n number of conditions. Now let's focus on the general form of these conditions. There are two sets of the conditions. One is the variable based, other is the multiplier based set of conditions. Coming back to this derivative, it says that if we have a Lagrangian function that we have developed in the process of optimization using the non-linear programming, it can be differentiated with respect to each of the independent variables, that is j variables in this case. And if we take these derivatives, all of them should be equal or less than 0. This is the requirement in this certain condition. The second part of it suggests that there is non-negativity of these variables, that these variables are non-negative. They can be either greater than 0 or equal to 0. This is suitable for our economic analysis, because in economic analysis the variables usually are non-negative. For example, investment and income, these are the variables that are likely to be positive or at minimum 0, but should not be negative. In the next column, we will merge these two terms in such a way that we are considering that if either or both of their values are equal to 0, then the product of these two terms will be equal to 0. In other words, if the product is 0, either one of them or both of them are 0. This is known as complementary slackness condition, as mentioned here. It is known as complementary slackness because there are two of the terms that are complementing each other to play the role of slack. And a slack variable is actually a variable that is used to convert inequalities into equalities. So here the same is happening, that these inequalities are being converted into an equality and they are complementing each other in order to equate it equal to 0. This basically is a mathematical thing. However, it can be useful for us to evaluate the values of x and y, or all those independent variables that we want to know, which are the critical values that can lead to the optimized value of the dependent variable. So this is why we call it complementary slackness condition. Now the other set of conditions is multiplier based condition, and here the same Lagrangian function will be differentiated with respect to the multipliers that we have used. And we have I multipliers here. It means that we have a number of constraints, and let's assume that it goes up to a certain number, and we will use all those multipliers here to differentiate. When we differentiate the Lagrangian function with the multiplier, the answer would be either equal to 0 or greater than 0. This is the condition or the requirement. And when we consider the non-negativity of the multiplier, it means that we can say that their product will be 0 when either of them or both of them are 0, so that the product becomes 0. Again, it is a kind of situation which we can call as a complementary slackness condition, where both of the terms are complementing each other in order to give rise to an equality on the basis of the given inequalities, and hence the phenomenon of slackness is visible, where some inequality is converted into equality by adding a variable which should be positive, and you can see it is being considered as a positive value, because a positive slack variable is welcome, negative slack variable is not, because it does not satisfy the constraint. Now we come to the numerical example which will unravel the things more. Here we have an objective function which is utility function, and it is a nonlinear function because the degree is 2, and we have general constraints that the consumption of both of the goods should be, when we sum them, should be at max equal to 100 or less than it, and the consumption of good X should be at max 40 but not greater than that. It can be less than that. Non-negativity constraints, as we have studied in the linear programming, they will also hold here, so that we land in the first quadrant, which is something very useful and usual for the economic analysis. And now we perform the first step, which is to form the Lagrangian function. We have two constraints, these general constraints we are talking about. Non-negativity constraints will not be as such used in the development of Lagrangian function. They will remain there as they are, and they will only guide us about the location of the graph in the Cartesian coordinates, that is the first quadrant. So if there are two constraints, there will be two multipliers, lambda1 and lambda2. Now you can see that we have formed the Lagrangian function. Z is a function of x and y, those two goods that were there in the utility function, and we have first multiplier, second multiplier, because the objective function is now added with this term, which is the first constraint, molded in a way where the constant remains in its place, where the variables, they get shifted to the right hand side, and hence this is equal to 0. The equality turns into this. Here we have its multiplier, the first multiplier, hence lambda1, and then we add another multiplier and its product with the second constraint. Second constraint, in that x is shifted from left hand side to the right hand side, so this term is equal to 0, and the multiplier is there. So if we multiply lambda2 with 0, it will not have any effect, neither will this lambda1 when gets multiplied to this term. So all of this term will be equal to 0. So we have not distorted the equality of the objective function. Actually it is the same, and this addition is basically neutral, doesn't affect the overall equality, just introduces the two multipliers that can be helpful for us. So the step 2 will be to use those Kuhn-Tucker conditions, and now we are going to use those conditions. There are actually two variables, x and y, and there are two multipliers, lambda1 and lambda2. So we will form the variable based conditions and then the multiplier based conditions. These are the variable based conditions, these are the multiplier based conditions. As we already understood that the number of variables will be equal to the number of conditions, so there are two independent variables, so there are two conditions, and if there are two multipliers, there are two conditions. Simply we had to differentiate the Lagrangian function with respect to the first independent variable and then the second independent variable, the answers of which should be less than or equal to 0 as per the required condition. And then the non-negativity of those two variables is mentioned as we did before, and their product will be equal to 0 if either of them is 0, that is the first term, that is the derivative, or the non-negativity values. Now the multiplier based conditions are also formed in the same way. We take the Lagrangian function and we differentiate it with respect to the first multiplier and then with respect to the other multiplier. The answer should be either positive or equal to 0, and the non-negativity of those multipliers should be mentioned, and their product will be 0 if either of them is equal to 0, which is the complementary slackness situation. Now developing the first order conditions, we have the same function, that is the Lagrangian function, which had this objective function and then the product of the first constraint with the first multiplier and then the product of the second constraint with the second multiplier. So as per the condition, this should be less than or equal to 0. We have differentiated this thing, simplified it, so we got this result. That you can do simply by pausing the video and viewing that how this simple differentiation and simplification is done. Now we have the other condition in which we had to differentiate the Lagrangian function with respect to the second independent variable. So this is the Lagrangian function getting differentiated with respect to the other variable, and it should be less than or equal to 0. And in the next step you can expect that we will be getting the result of it. So this is the result of it. You can pause the video and verify if it is correct. Then the other two variable, these were the two variable based conditions. Variable, let us mention it here, that these are the variable based conditions, and here we have the multiplier based conditions. So clearly the Lagrangian function getting differentiated with respect to the first Lagrangian multiplier and then with respect to the second multiplier, and the same process is done, the objective function and then its differentiation with respect to the multipliers. So solving this is going to be equal to this. After simplification we will get this expression. Now we have 4 of these conditions that are still in the form of inequalities. However, we are more convenient with the equalities when it comes to the solution, so it's better to convert these inequalities into equalities. This is the set of those values that are now converted into equalities. We are dropping the inequalities and we are going to opt for the equalities. These signs are now dropped and we are retaining the equal sign only. So the boxes are clearly mentioning that we have converted the variable based conditions and the multiplier based conditions into equalities. Now it is easier to solve them. As we can see, it is a simultaneous set of equations. We have 4 equations and we have 4 unknowns, so we can solve them simultaneously. In nonlinear programming we have 2 ways to do this. We have basically 2 trial solutions, and these are trial solutions, that is case 1 and case 2. For case 1 we assume that lambdas, that is the multipliers, they are positive, and for case 2 we assume that the variables are positive. So we can say that this is multiplier based trial solution, and this is variable based trial solution. So for the multiplier based trial solution, if lambda 1 is positive, then for the complementary slackness, the other term, that is this term in this product of lambda 1 and the derivative of the Lagrangian function with respect to lambda 1 can be 0 if this term is equal to 0, as lambda is already not equal to 0, that is, it is positive. Similar holds for the next multiplier based trial solution, that is, if lambda 2 is considered greater than 0, that is, here we considered it. So if lambda 2 is positive, then in this product this term should be 0 if the product is to be 0, fulfilling the requirement of the complementary slackness. So summarily we can say if both these multipliers are positive, then these derivatives will be required to be equal to 0. Now we come to the variable based trial solutions, in which the two or all those independent variables will be considered positive. So firstly we consider that x is positive. When x is positive, then in this product this term should be equal to 0 if this product is to be equal to 0, that is, to fulfill the requirement of complementary slackness. Now we have y, the positivity of the other independent variable, that is y. So if y is positive, then this product can be equal to 0 only if this term is equal to 0. So this can be summarily written in this row, that is, if both x and y are positive, then the Lagrangian functions, their derivatives with respect to those independent variables respectively, will be equal to 0. Now these two equalities equal to 0, that is, and these two equalities can be used to solve the simultaneous equations that we had. So since this is the first trial solution method we have, so we will use this first, in which the multipliers were assumed to be positive and hence these derivatives were found to be 0. So we will substitute these values into those equations. In those equations, this was on the left hand side and this was on the right hand side. So the right hand side is assumed to be 0 in this case, so we can now write 0 instead, and this is the final form of it after substitution. If you want to recall, you can go back and see those 4 conditions. In that, this was the condition that we are talking about. This is the third condition out of these 4 conditions, and the next one with respect to lambda will be the 4th condition out of the given conditions. So after verifying this, we can come to the same thing, that is, this is the 3rd condition and this is the 4th condition out of those. So you can go back to that slide and you see that this was the value of the 4th condition, and now it is equated to 0 by using the trial solution 1, that is the multiplier based trial solution, and from here you can easily extract the value of x, which will be 40. Here the value of y was written in terms of x, so we can put the value of x from there and then we can get the value of y. So now we have both of the values, that is x status and y status, those critical values of x and y. They are 40 and 60, and there are 2 other unknowns in the simultaneous equations, and they are the multipliers, that is lambda 1 and lambda 2. So we should solve for them as well by using the values of x status and y status, and they will be substituted in the other 2 conditions. This was the first condition out of the 4, and this was the second condition out of the 4. Furthermore, these derivatives now are equated to 0. This means that there is a positive value of y, due to which this value should be 0 for the complementary slackness to hold, that is, this product should be equal to 0. So y is positive. Why we can say this? Because y is 60. So y is already found to be positive. So this term has to be equal to 0 in order to fulfill the complementary slackness. Here similar thing will happen, that this term should be equal to 0, and why it is equal to 0? Because x is positive. X is 40. So it is now confirmed that it is a positive value. Therefore, in the product of these two, this term has to be equal to 0, just like we did in this case. So we have developed the logic for having these two derivatives, that is the derivative of the Lagrangian function with respect to y and derivative of the Lagrangian function with respect to x equal to 0. So we are going to use the first and the second conditions here. So we can solve them easily. This one will give us the value of lambda, because it's easy to extract the value of lambda as x is equal to 40. So if x is equal to 40, it means that we can put here the value and lambda will be equal to 40. Then we have to find the value of lambda 2, for which we know the value of y, which is 60, which is already found, and lambda is also found, and that is equal to 40. So the lambda 2 is now found to be equal to 20. Lambda 1 and lambda 2, both of them are now evaluated. Now we can use all four of these values, that is the value of x and y and lambda 1 and lambda 2, to verify if we have actually found the critical values, or those values that will maximize the utility. So let's start from the objective function. This was the objective function. If I put the value of x and y, then the answer will be 2400. So this is the maximized utility. If we consume 40 of x and 60 units of y. And these are the general constraints. The first constraint was this. So if we add these two values that we found of x and y, it will be either equal to 100 or less than 100. So it is equal to 100. Then the general constraints, they are there. X is not less than or equal to 40. So here we found that the value of x is actually 40. So it is not violating the constraint. It is equal to 40. Non-negativity constraints, they are fulfilled because both x and y, they are positive. They are non-negative. That is, they are either equal to 0 or greater than 0, and in this case they are actually greater than 0. So all of the constraints, they are met, and the undisputed values of x and y they are 40 and 60, and the maximized utility is 2400 units. So this is how we do the nonlinear programming. We took a maximization situation of a utility function for which there were multiple, that is two constraints. Two constraints were developed for making the justification of non-negativity, and there were two multipliers they were found, that is lambda 1 and lambda 2, and we used the complementary slackness condition to find their values, and we also resorted to trial solution, which one they were based on the variables and multipliers, that is multiplier based trial solutions and variable based trial solutions. And before that we developed those conditions using the Kuhn-Tucker conditions, and we developed the Lagrangian function before it, and this is how the nonlinear programming for the sake of maximization is done. In the next video we will do the nonlinear programming for the sake of minimization of a certain variable. Thank you.